I'm Marina from the Faculty of Physics of the University of Rijeka, where I am an associate professor and I work in multi-wavelength and multi-messenger astrophysics since a lot of years. I will put the timer for me as well. So today I'm going to talk to you about camels. I think you know why. If not, I will give you some definition, so it will be easier. So my camels in the sky, they can have one hump or two humps. So usually I work with camel, not with dromedaries, but I work with camels. So I have two bumps to work with. And those bumps are, of course, multi-wavelength or multi-messenger spectral energy distributions. So since many years, what I do is to collect multi-wavelength data, possibly multi-messenger when it's possible, and then work on the emission mechanism of the sources. So trying to put together an interpretation of the multi-wavelength data set. So just to shortly, what happens is to get to the camel, so to the spectral energy distribution, you need to start with multi-wavelength light curves. This is just an example. I mean, I could show you this paper exactly, okay, but now it's complicated. Anyway, I took just one recent paper with multi-wavelength analysis. And okay, we have light curves from different instruments over time, of course. So we have these intensity, these signals from different instruments. We check them together, and then from multi-wavelength light curves, we build multi-wavelength spectral energy distribution, meaning the camels. So what is the problem here? When we collect multi-wavelength data, so the main problem is finding those data. You want to be them more simultaneous as possible, which is already tricky. So there is a lot of work trying to put together all this data. A lot of data, as we have seen in the last days, as we know, they are public, so this is easy to do. When data are not public, it's less easy. So it's a big struggle trying to put together as much data as possible. So in this example, you have, okay, a decent coverage because this is Markarian 41, which is a lot observed. But in other cases, as I will tell you, this is really complicated. So, okay, from light curves, we go to spectral energy distribution. So we go to the camels. This is from the multi-wavelength light curves we have seen in the slide before. So it's the same work. And focusing on one event in this multi-wavelength light curve, we say, okay, we want to study exactly this time period with simultaneous data, and then we build a spectral energy distribution, which is, I mean, it's quite easy. When you have the data, this doesn't take much time. And so with this spectral energy distribution, that when you have high energy data, it's a camel, otherwise would be a dromedary, but I focus on this, on the camels. When you have multi-wavelength spectral energy distribution, then this is what you need to understand the astrophysics behind the source. So what really happened there? And you do it, of course, modeling, using theoretical models to model the camel. Okay, here, this is from the paper before, so there are quite, how can I say, there are enough points to constrain the theoretical models, but many times you don't have enough points to constrain theoretical models. So basically you can model whatever you want, whatever interpretation works. But okay, in this case, the modeling was fine. But this is just an example. So camels, when we have dromedary, everything is fine. We know this is synchrotron emission. So the first bump, I mean, it's quite, everybody knows what it is. The problem is with camels because the high energy bump, okay, we say it's the inverse Compton bump, but if you use a simple theoretical model, you know, electronic model, this doesn't always work. So the high energy bump is like, I would not say a mystery, but it's not so easy to understand. Okay, So there are many emission models. You want leptonic. So you assume there are electrons, you know, moving around the gravitational field of the black hole or whatever. So, okay, you have density of electrons, then you have leptonic, but of course you don't know. Maybe there are protons, there are other stuff. So leptonic model sometimes doesn't work. Then you have hadronic model. Then why not you can have leptohadronic models? So, I mean, there are a lot of things that you can do to model a camel. And sometimes all of these things that you do, they work, all of them. So you really don't know what is going on there. Yes, you have, this is again about models. Why this happens is because our theoretical models that we use to understand the emission mechanism of sources, they have a lot of parameters, of course. So this is just an example of some parameters that you have. You can, of course, fix some parameters from the literature, but anyway, you fix something, but you cannot fix everything, you are not sure. So there are a lot of possibilities. The good thing is that now there are a lot of tools that can be used by everyone trying to model. You know, we have JetSet, we have AGMPy. There are several tools that we can use, but at the end, you have so many possibilities that you can try. You do the best that you can do, but at some point you need to call a theoretician because there is a moment in which there are too many things that work, and then you need the theoretician to confirm or not, or help you to construct the model. So now I give you some, very fast, I give you some example of my struggles with multi-wavelength data. And you can see it's 10 years that I work with this data, but I am never really satisfied with what happens. So in this case, we worked in, you see how many data we have here. That was a very interesting flare of an AGN. And even if we collect, we try to collect as much data as possible, still we have a lot of holes in those light curves. Of course, we did our best, identifying 2 periods in which we had more simultaneous data. But then this work was very interesting for many aspects. But then the camel came out like the best model that we could produce was not perfect. And in that case, it was a one-zone model. So you can see that if you check the model, which is the black curve, you see that the high energy pump is not well fixed. But we couldn't do more than that at that time. So is this model constrained? No. So we need to find another model for that. Here I put radio curves, radio maps. Why? Because together with multi-wavelength data, you can also have fantastic radio maps from radio colleagues. But then it's very hard to connect the morphology that you see in radio with the multi-wavelength data set, because you know, there are a lot of problems here in the sense you could see some evolution in radio, but then theoreticians say, okay, but we cannot really connect to this, to the emission. So it's very difficult to use radio data, even that they look very, very helpful. Another example, okay, another source, super interesting flare in very high energy. So we try to collect a lot of multi-wavelength data. Also here, a lot of holes everywhere, but okay, even here we did our best. We have our camel, we modeled, is the model constrained? Well, yes, in the sense we learned a lot of things from this source, but also here, the leptonic model has to have an external component, and this can be explained in many ways. So it's not really constrained. Did we see this source again? No, we could detect it only once. So we cannot even try to make this better because we didn't observe this anymore. Another example, same thing, beautiful source, fantastic flare in several wavelengths, some more holes in the light curve. even here we did our best. We have the camel. You see now the camel, the bump is going up. So this camel has a big Compton, yeah, I forgot the word, but I mean, when the high energy bump is higher than the synchrotron bump, then this is a message that this source has some process that accelerates to very high energy gamma rays in a peculiar way. Also here we have a model. Is this definitive? We don't know because we never observed this source anymore. So also here, you know, when these flares are very, you know, you don't have them anymore, it's difficult to understand really the emission mechanism. Again, another example, this was a gravitational lensed blazer, light curve terrible. I mean, what can you do? We tried to collect simultaneous data. This is the best we could do. There was another that was trying to get other data, but this is the best we could do. Anyway, we learned a lot from this gravitational lensed blazer. Here we have, again, strange camel. This is huge Compton dominance. Now I remember the word. And here we tried this model. Actually, it works very well, but we didn't observe it again. So we are still waiting to try to connect with new data from this source. And this is my last paper. Again, another blazer with a very fantastic flare in very high energy. But then what happens when you try to connect, try to do a theoretical interpretation of the camel, then you are left with all the models work, whatever. So the very you know, big frustration from it. So you have multi-wavelength data, you have a spectral energy distribution, you have your camel, but then it's very difficult to constrain the models. So also here, we will probably try to find other theoretical models. Okay, well, this is my struggle. Very difficult to give a theoretical interpretation because of the it's difficult to find the simultaneous data or to collect them. But okay, with multi-messenger astronomy, here I go very fast. After, you know, this important source that we have heard about it many times in those days. Then we started with the first multi-messenger study, including blazer and neutrino. Also here, multi-wavelength light curves. This is what we got. I mean, simultaneous data are not so many. Anyway, of course, this is a fantastic event from which we learned a lot of things. But in terms of camels, the modeling of this source was quite, you know, difficult. So we have different theoretical models that were applied. This is one of the most famous, leptohadronic. And here you can see we have a special camel with three arms. But we saw only one of these mythological animals. So we are waiting for the next camel with three arms. And gravitational waves. Also here we had one single multi-messenger event. I don't have the camel here. It was very important, but it was quite some years ago. So we need something new soon. What I want to say, what is my message? Why it's so confused? Because I'm very confused. It's 10 years that I'm trying to have a theoretical explanation of what is going on with the sources that I study. And this is never really defined. So I cannot never say, okay, this model works. So what is happening here is this and that. I have this black hole, I have this density of particles, they are doing this, they are doing that. I cannot say it because it's very difficult to constrain the theoretical model. So what is my point? To make this really physically important, we need to have data which they have to be as much simultaneous as possible. What does it mean? We need to coordinate to get this data. And this we know, we try many ways. We have a lot of alerts. We have Astro-COLIBRI to be also more sure of what it happens. But then if your sample, if your light curves have a lot of holes, you cannot really infer a theoretical interpretation. If data are not open, it's a mess, because then you need to wait for other people to analyze this data. And this can take forever, like it can take years. And this is terrible. And so what can we do? I really don't know, because it's important that we coordinate. But I think at this point, if we coordinate on everything, then what we get are light curves which have a lot of holes, because of course, you trigger alerts on different things, but then people spread on those alerts, and you cannot get a data set which is meaningful. So my idea is maybe the coordination shouldn't be only in getting data, spreading with others and stuff like that, but it should also be a bit before, trying to have some proposal which is not separated in different instruments, but some like a keynote proposal that puts together different telescopes, because maybe in this way we can get multi-wavelength data which are really good, you know. Or as Fabian was saying yesterday, a good thing would be to have more connection with people in order to, you know, trying to get samples which are more meaningful. I don't know. So we need better data sets, in the sense, more simultaneous data. We need open data. We need better sampling and data formats which are compatible between bands. So this is what is my message here. I don't have solution, just a lot of frustration, but okay, that's it. Thank you.